Okay, so let's look at a topic called a Galois or a Galois field. And we're going to perform some operations, addition, multiplication and division. And hopefully we'll be able to understand how we use Galois fields to be able to simplify our computation within inside cryptography and in areas like data communications. Before we do that, we need to understand what a group, a ring and a field actually is. So within cryptography, we define what's called a finite field or a Galois field or GF. The number of elements that we hold becomes our Galois field number. So in this case, we might have 7 elements. That's a finite field of 7 elements. And what should happen is that we form a ring with those elements so that we never go outside of the ring. We will ring round for our operations or roll over. So within our finite field, in this case, we have 7 elements. So we might have an object or an entity A and another one B. And we're going to map that into another group through some sort of operation. And it's this operation that defines our field. To make a field, then we must perform certain operations. So additive, we might take an entity in one group, add another one to it, and then we'll map to another value within inside the ring. And in cryptography, we need to make sure that there is unique mappings from one group into another. We can also provide a subtraction. We might subtract A from B, and that will map into our group. We should be able to multiply and also divide. And then we have the operations, the A something B is equal to B something A there. And that operation might be add, subtract, multiply, or divide. Doesn't matter if we do A something B or B something A. And we also get the operation where B something C something A is equal to A something B something C. And we could replace these operations here and still get the same result. Another operation that we need to perform is the inverse, where we take an entity from our group, and then whenever we perform an operation such as a multiply and we take the inverse, then the result will be 1. Okay, so our Galois field allows us to be able to limit the number of entities that we have within our group and then perform these operations within our finite field. So with the Galois field, we can have 2 different types. We can have a Galois field of P, where P is a prime number. So we might have GF of 7 or 2 or 3. So with a Galois field of 2, we only have 2 entities, a 0 or a 1. Okay, so we might take A and B, either a 0 or a 1, and we'll map to an output of Z, and that's also equal to a 0 or a 1. So a Galois field is like binary operations, but on a single bit value. The other Galois field is where we take a prime number and raise it to a power of m. In this case, we'll have p, a prime number, to the power of m. So one example is here is 2 to the power of 4 will give us 16 different elements. They could go, for example, from 0 up to 15, and because we have a ring, we will go round again. And the great advantage of this is that it limits the number of bits or the number of elements that we're operating on at a time. So it should significantly reduce the complexity and the speed because we're only looking at very small elements. The GAF of 2 is very common and is often known as modulo 2 operations, as we'll see in a little minute. So with modulo 2 operations, we basically just have two simple things. We have an XOR, or we have a multiplication operation. This is known as XOR, and this is known as an AND or a multiply operation. This is also known as an add operation. But the thing with modulo 2 is that we don't have any carries. So normally when we would do our adding, we would have a carryover for each of the units. But in modulo 2, we only look at 1 bit value at a time, and the same goes for our AND operation. So this keeps it very simple in that we don't have to worry about the carry operation that we have. So in modulo 2 addition, it's similar to an adder, but we forget about the carry over from the 1 plus 1. So 1 exclusive OR 1 gives us 0, 0 exclusive OR 0 gives us 0, 0 exclusive OR with a 1 gives us 1, 1 and a 0 gives us 1, and 1 and a 1 gives us 0. With modulo 2 we ignore that there's a 1 carried over, because normally we would have a 1 here, but we ignore that. With a multiplication, that's with the AND operation, a 0 times 0 gives us 0, 0 times 1 gives us 0, 1 times 0 gives us 0, and 1 times 1 gives us 1. If we look at addition when it comes to multiple bits, we take each one at a time. So 1 add 1 gives us 0, and we forget about the carry. Now 1 add 0 gives us 1, and so on. And we only look at the columns there. We never look at the carry over that we would do in normal addition. With a multiplication, 1 times 1 is 1, 1 times 0 is 0, and so on. Here we have a 1 times 1, so it gives us 1 there. And with this, we keep it simple and it can become fast. And the great thing with this is that we can run these in parallel, these operations, because we're not depending on the carry forward bit that we would normally have in our normal addition and multiplication. So within this Galois field, we can have 2 to the power of m. So 2 is the prime number, 2 to the power of 4 will give us 16 different elements. And we can then represent our bits as a polynomial equation. So if you remember that a polynomial equation looks a bit like this, 5 plus 2x squared plus 4x cubed, and so on. These are polynomial powers that we have. In our field here, what we have is that we can represent our bit patterns with a polynomial value. And then the advantage with that is that we can operate as with polynomials on our calculations. So in this case, we have our 1s, and that's x squared, x cubed, and so on. So in this case, 1, 0, 0 becomes x squared. 1, 0, 1 becomes x squared plus 1. 1, 1, 0 becomes x squared plus x. And we can see we can represent our bit values as a polynomial value. Then when we're adding, if we're adding x squared plus x squared, that becomes a 0 because they cancel each other out, as we have with XOR operations. So it's with these operations that we can then perform our adding and multiplying operations. Okay, so let's take an example where we have a equal to 1, 1, 1, or decimal 7. That will be x squared plus x plus 1. And the b value is x plus 1, which is 0, 1, 1 in binary. And then what we have is a bit pattern called a primitive. In this case, it's called an irreducible primitive, and it's a bit like a prime number in our normal a representation of integers. If we have a value of 16, it's equal to 2 times 2 times 2 times 2. 14 becomes equal to 2 times 7. Every value is represented by the multiplication of prime numbers. In this case, our primitive is a value that's like a prime number. It cannot be factorized into other polynomials. So we're using a primitive here, and what we use that primitive is that if the value of the output goes above our limits for the powers, then we will divide it by this primitive to be able to get a value which will be within our polynomial space. And I'll show that in a little minute. So to add, it's quite easy because we add the powers, and we have x plus x here. These will cancel out, and then we'll have a 1 there, and again 1 plus 1 will cancel out, so our end result is x squared. Now if we multiply, if you remember, multiply that one by that one, that one by that one, that one by that one, that one there, and then there, and then there. So that gives us x times x is x cubed, x times 1 is x squared, x times x is x squared, and so on. And now we see that these two cancel out, and these two cancel out, and we get the value of x to the power of 3 plus 1. There is no need for us to divide by the primitive because we are constrained within the polynomial range, and the value here is less than the polynomial range. So we don't need to divide by the primitive. So here's the results here that we get. There's a primitive, there's the a and the b value, and when we add we get x squared, and when we multiply we get x cubed plus 1. If we look at our code, this is the code that will allow us to do this. This is our Python code, and we've got various operations. So we're representing our values as integer arrays here, and the same with our primitive. We then convert them into the Galois fields here with this method, and then after that we can then basically just operate on them with our arithmetic operations. Okay, so we can have a look at this code. Okay, so this is the example here where we have 1, 1, 1 and 0, 1, 1, and this is a primitive here. We'll just run that there, and there's the output that we get there. Just to show that we can change that. There we go. But this is the value here that we get. Okay, so the code that we're using is this code here. If you want to see this running, then there's a Replit site here. But what about the divide operation, where we're dividing A by B? So for this, what we do is that we find the inverse of B and multiply it by A. So that's equivalent to A divided by B, but we take the inverse element. And as we have with our field, we should be able to find the inverse of our polynomial. So in this case, we have that, and our Python program has found out that the inverse is x cubed plus x squared plus x. And then we multiply that out, and we should get this here. So from this, we can see that x to the 4 cancelled out, x to the 3, that cancels, but you can see there's still another one there, so that will be okay. And then the x squared is cancelled out there, and then we end up with x to the 5, x to the 3 plus x. But the result that we get isn't that. And the reason for that is that we have now a power which is greater than our primitive power of x to the 4. So we now take that value and we will divide it by our primitive value and take the remainder as the result. So if you remember your long division, so x to the power 4 plus x plus 1 goes into x to the 5 plus x to the 3 x times. Then we multiply that to give x to the 5, multiply that by that, x squared, that by that is x. So then we subtract them, subtract, get that, and then that will be removed. So we'll end up with x cubed plus x squared, which is the result that we have here. Okay, so that's the add. The subtract is just the same as add. Multiply, we've seen the operation, and then the divide in here. So now let's look at another one where we will end up in the same way with a power greater than or equal to x to the power of 4 when we multiply. So with this one, we'll take x cubed, which is 1 x to the 3, no x to the 2, x to the 1, and those 1s. So that will be x to the 3. And then we'll take b as x squared plus 1, x squared plus 1. And we'll take the same primitive, and we have a Galois field of 2 to the power of 4. So our add is quite easy. It becomes x cubed plus x squared plus 1. So that's that one correct there. Now our multiply becomes x cubed times x squared plus 1. And then that becomes x to the 5. And then we'll have x to the 3. So now we have a power which is greater than x to the power of 4. So we now need to divide that by our primitive. So again, we do the same. X to the power of 5 plus x to the power of 3 divided by x to the power of 4 plus x plus 1. That goes into that x times, so we end up with x5, x squared plus 1. and then we'll subtract them. We get nothing here. That becomes x to the power of 3. That becomes x to the power of 2. And that becomes x. That just becomes x. So the minus is just the same as a plus in modulo 2. So we can see here that divide operation gives us this result here. Okay, so in this way we can make sure that that our values, we can do our multiply. So this is a multiply in here, and we could do the same as we did before with the divide, where we would find the inverse, and then we multiply the inverse by our a value, and then again we'd have to divide by the primitive to give us this result here. One example of using Galois fields is an AES encryption, and the advantage with this is that we only deal with 8-bit values at a time. So we operate on a byte value, so we end up with a Galois field of 2 to the power of 8, and then we can represent our values in the form of a polynomial. The primitive that's actually used in AES is this one here, and this is the value that's obviously used to be able to constrain the values that we have. So this is the great advantage, is that we can make our operations run in parallel, but only on 8-bit values, which keeps the circuitry and the speed fast, as opposed to running on public key encryption, which can take hundreds or thousands of bits at a time. Okay, so that's been an introduction to addition, multiplication and division in Galois fields of GF of 2 to the power of m.